G'day and welcome back. Today we're looking at latent heat. Latent is just an old word for hidden, so this lesson is about hidden energy. Energy that goes into water but doesn't show up on a thermometer. Sounds strange, I know. By the end, you'll be able to calculate exactly how much energy it takes to melt ice or boil water, and you'll know why the temperature sits perfectly still while it happens. Let's take it slowly, step by step. First, a definition. A phase change is when a substance changes state. That's all it means. Solid to liquid is melting. Chemists also call it fusion. Same thing, two names. Liquid to gas is boiling or vaporisation. Again, same thing, two names. Now here's the big idea of the whole lesson. During a phase change, the temperature stays constant. Constant means it does not move. Not up, not down, flat. Picture a glass of ice water. The ice melts at 0 degrees, and while there's still ice in that glass, the water sits at 0 degrees. You can heat it as hard as you like. The thermometer doesn't budge until the last bit of ice is gone. Same with boiling. Water boils at 100 degrees, and it stays at 100 until every drop has turned to steam. Have a think about that. Where is all that heat going if the temperature isn't rising? That's our next board. Water molecules are a bit like friends holding hands. They grip each other with something called a hydrogen bond. A hydrogen bond is a weak attraction between one molecule and its neighbor. Between, that's the key word. Careful now, this trips people up. The bond inside a water molecule, oxygen to hydrogen, is a strong covalent bond. That one never breaks when water melts or boils. It's only the weak hand-holding between molecules that lets go. Look at the diagram on the right. Solid lines inside molecules, dashed gold lines between them. Two different things. Got it? Good. So, melting. The heat energy goes into breaking some of those handholds so the molecules can slide past each other. That's a liquid. Boiling breaks the rest and the molecules fly apart completely. That's a gas. And that answers our question. During a phase change, every bit of energy is busy breaking bonds. None is left over to raise the temperature. The energy is hidden in the bonds. Latent, hidden. See how it all connects? Here's our equation for phase changes. Q equals M times L. Three symbols. Let's define each one right now. Q is the heat energy. We measure it in joules. A joule is just a unit of energy, like a dollar is a unit of money. M is the mass, in grams, how much water we've got. And L is the latent heat. It tells us how many joules each gram needs to change phase. So its unit is joules per gram. There are two values you need for water. For melting, we use LF. The F stands for fusion. It's 334 joules per gram. Every single gram of ice needs 334 joules to melt, like an entry fee, per gram. For boiling, we use LV. V for vaporization. It's 2,260 joules per gram. Now pause and compare those. Boiling costs about 7 times more than melting. Why? Think back to the hand-holding. Melting only loosens the grip. Boiling has to break every handhold completely and fling the molecules apart. That takes far more energy. Makes sense, doesn't it? Now, you already know another heat equation from our last lesson. So, we have two, and the most common exam mistake is mixing them up. Let's make the rule crystal clear. When the temperature is changing and the phase stays the same, we use Q equals mc delta T. Quick reminder, C is the specific heat capacity, how much energy 1 gram needs to warm by 1 degree. Delta T is just the temperature change, finish minus start. When the temperature is constant and the phase is changing, we use Q equals ml, one job each. They never work at the same time, so before every question, ask yourself one simple thing. Is the thermometer moving? Moving, mc delta T. Flat, ml. Say that out loud once. Moving, mc delta T. Flat, ml. Lovely. That one habit will save you marks all year. Let's put the whole story in one picture. This is called a heating curve. Along the bottom, energy going in. Up the side, temperature. We start with ice at minus 10 degrees and just keep adding heat. Watch the right side as we go. Section A. The ice warms up. The line climbs. Thermometer moving, so that's MC delta T territory. Section B. We hit 0 degrees and the line goes flat, completely flat. The ice is melting and every joule is breaking hydrogen bonds. Flat thermometer, so this is MLF. Notice both solid and liquid exist together here. Section C. All melted. Now the liquid warms from 0 to 100 and the line climbs again. Section D. Flat again at 100 degrees. Boiling. This is MLV, and look how long this flat section is compared to the melting one. About 7 times longer, because LV is about 7 times bigger. The graph is showing you the numbers. Section E. All steam now, and the gas keeps warming. So remember, sloped sections, temperature changing. Flat sections, phase changing. Every heating curve question comes down to reading that. Still with me? Beautiful.
Time to use it. First worked example, nice and gentle. How much energy do we need to melt 50 grams of ice at 0 degrees? Write down what we're given. Mass, 50 grams. And since we're melting, we grab LF, 334 joules per gram. We want Q, the energy, in joules. Now our habit question. Is the thermometer moving? No. The ice starts at 0 and melts at 0, flat. So it's a phase change, and the equation is Q equals MLF. Substitute carefully with units. 50 grams times 334 joules per gram. Notice the grams cancel out, leaving just joules. That's how you know your units are right. 50 times 334 is 16,700. So Q is 16,700 joules, which is 16.7 kilojoules. Box it. Done. See the rhythm? Given, to find. Check the thermometer, formula, substitute with units, box the answer. Every example today follows that same rhythm. Second type. 20 grams of water, already at 100 degrees, turning completely into steam, still at 100 degrees. How much energy? Given. Mass, 20 grams. We're vaporizing, so it's LV this time, 2,260 joules per gram. We want Q. Thermometer check. Starts at 100, ends at 100. Flat. Phase change. Q equals MLV. 20 grams times 2,260 joules per gram. Grams cancel again. 20 times 2,260 is 45,200. So 45,200 joules. That's 45.2 kilojoules. Box it. And pause on that for a second. Just 20 grams, a few tablespoons, needs 45,000 joules to become steam. Almost 3 times what 50 grams of ice needed to melt. Steam carries serious energy. Hold that thought. We'll use it when we talk about sweating. Now the big one. This is the 8R level question, and it's the one that separates students who plan from students who panic. 10 grams of ice at minus 10 degrees, taken all the way to steam at 100. Look at everything we're given. 2 heat capacities this time. C for ice is 2.1 and C for water is 4.18, both in joules per gram per degree, plus our 2 latent heats. 4 constants means the examiner expects 4 stages. Here's the golden rule. 1 journey, 4 stages. We calculate each stage on its own, keep them separate and only add them up at the very end. Never squash stages together. Stage 1. The ice warms from minus 10 to 0. Is the thermometer moving? Yes, up 10 degrees. Same phase, still solid. So this stage is MC delta T, using C for ice. 10 grams times 2.1 times a change of 10 degrees. That's 210 joules. Write it down as Q1 and leave it alone. Stage 2. We're at 0 and now the ice melts. Thermometer flat. Phase change. Switch equations. MLF. 10 grams times 334. That's 3,340 joules. Label it Q2. 2 stages done, 2 to go. Notice how each stage picked its own equation? That's the whole skill. Stage 3. All liquid now, warming from 0 to 100. Thermometer moving, so back to MC delta T. But careful, we've changed substance behavior. It's liquid water now, so we swap to C for water, 4.18. 10 grams, times 4.18 times 100 degrees, that's 4,180 joules. Q3, stage 4. 100 degrees and the water boils away. Flat thermometer, mLV. 10 times 2,260, 22,600 joules. Q4. All 4 stages done. Now, and only now, we add 210 plus 3,340 plus 4,180 plus 22,600. That's 30,330 joules. Call it 30.3 kilojoules. Box it. Take a breath. That's a full 8-hour question, done calmly. And look at the bar chart on the right. Boiling alone cost 22,600 of our 30,330 joules. Roughly 3/4 of the entire journey just for that one flat plateau. Latent heat of vaporization is the heavyweight. Remember that picture. Right, let's take this into real life. Why does sweating actually cool you down? Have a guess before I tell you. Sweat is mostly water sitting on your skin, and we now know something powerful about water. For each gram to evaporate, it must absorb roughly 2,260 joules. That energy bill has to be paid by something. It's paid by your skin. The water pulls that heat straight out of your body as it evaporates. Heat leaves you, so you cool down. Simple as that. Let's put a number on it. Say 5 grams of sweat evaporates. Not much, a small splash. 5 times 2,260 is 11,300 joules pulled out of your body, from 5 grams. That's why sweating works so well, and it's all because water's LV is enormous. So here's your one-line summary. Evaporation is your body paying an energy bill, and it pays in heat. It's also why a humid day feels awful. The sweat can't evaporate, the bill never gets paid, and the heat stays with you. Last worked type, and it runs backwards. Ice in a cooler at a barbecue absorbs 100,200 joules of heat from the drinks. How much ice melts? This time we're given Q, the energy, and we know LF. The unknown is the mass. So, same equation, different unknown. Thermometer check first, always. The ice melts at 0 and stays at 0, flat. So Q equals mLF. But we want M, so we rearrange. Divide both sides by LF. M equals Q divided by LF. 100,200 divided by 334. Watch the units. Joules divided by joules per gram gives grams. The units confirm we're finding a mass. That's exactly 300 grams of ice melted. Box it. And here's the beautiful part. While all that happened, the ice never got warmer than 0. It soaked up 100,000 joules without its temperature rising at all. That's why ice is the perfect coolant. It's a heat sponge, and latent heat of fusion is the sponge. One more place this shows up, and it's a big one: the weather. The sun evaporates water off the ocean, gram after gram, and every gram carries away those 2,260 joules. The vapor is a flying battery, loaded with hidden energy. When that vapor rises, cools, and condenses into cloud droplets, the phase change runs in reverse. All that latent heat gets released back into the air. That released energy is what powers thunderstorms and tropical cyclones. A cyclone is, honestly, latent heat with wind. And fusion shows up too. Ever noticed snow takes ages to melt, even on a sunny spring day? Every gram needs its 334 joules before it can become water. The snow is quietly soaking up the sun's heat at a steady 0 degrees. Latent heat isn't just an exam topic, it's running the sky. Let's gather it all up. Phase changes happen at a constant temperature. 0 for melting, 100 for boiling. The energy goes into breaking hydrogen bonds between molecules, never the strong bonds inside them. Our equation is Q equals mL. Energy in joules, mass in grams, latent heat in joules per gram. 2 numbers to memorize. 334 for melting, 2,260 for boiling. And the habit that earns marks. Thermometer moving, MC delta T. Thermometer flat, mL. For the big journeys, 1 equation per stage, subtotals kept separate, and add only at the end. That's the whole lesson in 7 lines. If any line feels shaky, scrub back to that board and watch it again. That's exactly what the video is for. Your turn now. 5 questions, no solutions on screen, because the thinking is yours. Question 1 is a straight melt. Question 2 is a straight boil. Question 3 is a mini journey. Count your stages first before touching the calculator. That's the skill. Question 4 runs backwards, like our cooler. And question 5 is words, not numbers. Use LV in your answer. Pause the video here, work through them slowly, and check every unit as you go. Take your time. Speed comes later. Understanding comes first. Great work today. Latent heat looks strange at first. Energy going in with nothing on the thermometer. But now you know exactly where it goes and exactly how to calculate it. Next lesson, we bring heat capacity and latent heat together in full exam questions. Until then, you're mastering VCE chemistry, one concept at a time. See you next time.